All right, here's a little bit of information about the alkylation of dimethoxybenzene lab. There's a version in your loose leaf pages. What we're going to be doing is a little bit different. The main difference being that the alcohol is going to be different. The amounts are also somewhat different, and that's why I've provided a handout. So the handout that I've provided, first of all, there's some information on the Chem24 remote resources page. I no longer have my cute little pointer when I'm in the browser. So there's a link to a handout, which I just clicked on, and that will give you the procedure that you should have in your notebook, and that matches pretty closely the video, and I'll talk about that a little bit more. Now I'm going to go back, or try to. And so we have the handout, the pre-lab lecture that I'm currently doing, so there can't be a link to it. That would be impossible. Some information on recrystallization, a video of the actual alkylation lab, and then I provide you with the data that you need to use to write up the report, as well as the spectra. So now we'll go back to Notability. And so, again, we're going to start with the dimethoxybenzene, and we're going to react it with this alcohol, a racemic mixture of this alcohol that has one chiral center, and use sulfuric acid and acetic acid. And your mission is to determine what product is formed, which I'm not going to tell you at the moment. By the way, I've never quite figured out why we need the acetic acid, but I'm afraid to leave it out. And I notice in all the various procedures I found online with variations of it, they all use acetic acid. So we'll take a look at the beginning of the mechanism. So in the Klein book, the alkylation reactions are typically done with an alkyl halide and aluminum chloride to generate the carbocation. Here what we're doing is we're using an alcohol and acid. And so the acid, probably from the sulfuric acid, protonates the alcohol. That converts the OH into a good leaving group, which leaves and generates the carbocation. And so then the question is, what happens next? I'll give you a little bit of a hint. So again, here we have the dimethoxybenzene. It gets alkylated. And it turns out that in this initial reactant, all of the positions are equivalent. So it doesn't matter where we put the R group, we'll get the same product. And you can convince yourself that this is true. So I put it up here in pink. And then, for a variety of reasons, this starting material has two strongly activating groups on it, relatively strongly activating groups on it. And adding one alkyl group only makes it more reactive, plus there's an excess of the alcohol, and as a result, a second R group adds. Now, there are technically three positions where that alcohol could add. So the alcohol, not the alcohol, but the alkyl group from the alcohol could add. So in theory, you could put it between the first R group, the pink one, and one of the methoxys, and you can think about how likely that is. You could also put it over here, right next to one of the methoxys, and make this compound. Or you could add it para to the original R group and make this compound. And we're going to be using NMR to determine which product that you get. Notice that this bottom product has a lot more symmetry to it than the other two do. So a couple of procedural notes, and then I'll talk about the recrystallization. So in the online video, first of all, he uses a round bottom flask with a Kleisen adapter, and then attaches the addition funnel, not the additional funnel, it's a separatory funnel, uses an addition funnel to one of the arms of the Kleisen. In the procedure that I found online, it doesn't exactly match that. They actually use an Erlenmeyer flask, which is what we've typically done when we've done the similar reaction. And then you'll also notice that occasionally when you can actually see how much material is being used in the video, that the amounts don't match the video. That's fine. Just go ahead and use the video amounts, and then, excuse me, not the video amounts, use the handout amounts, and then also for the data, use the information that's on the remote Chem 24 webpage. So one thing I wanted to mention about the video is that apparently he had a stockpile of crude material. So what he does is he actually sets up the recrystallization with some of the stockpile material before he actually makes it in the video. And that's pretty confusing if you're not aware of it. I had to watch it a couple of times. But once you have the crude material, you need to recrystallize it to purify it. And recrystallization is a very common way of purifying a solid. So a couple of things before you commence a recrystallization, there are two things that you want to do, at least if you're in one of my classes, and that is you want to weigh the crude material. And the main reason I have students do that is that in case the recrystallization goes awry and they don't get any recrystallized product, that at least they have something that they can use for their data. In the real world of research, if you messed up your recrystallization, you'd redo the experiment, but we don't have time for that, assuming we actually had a lab to do it in at the moment. The other thing that I have students do is to save a teeny tiny amount. And we're talking about the amount that you would need to put in a melting capillary tube. And again, what you're doing here is kind of hedging your bets. In case the recrystallization doesn't work, that tiny amount can be used for a melting point, and therefore you don't have to redo the experiment. So when you do a recrystallization, the idea is that you want to set up an equilibrium. And the equilibrium that you're looking at is between the dissolved solid and the undissolved or not dissolved. I'm writing it as not dissolved because I think it's a little bit easier to see. And so this is similar to those equilibrium labs that you may have done in Chem 10 or Chem 12, where you set up an equilibrium and you sort of get it at that tipping point where it's really easy to shift back and forth. So you would set up your equilibrium and then you'd make some sort of a change, like with temperature, or you would add something, you'd get it to go this way and that way. And that's exactly what we're going to do here. So if you decrease the temperature, that's going to shift it to the not dissolved side. And if you increase the temperature, it's going to shift it to the dissolved side. And then also, if you add solvent, that's going to shift it to the dissolved side. And if you remove some of your recrystallization solvent, say by evaporating it, that's going to shift it to the not dissolved. And that last one is something that you can use if you inadvertently use too much solvent, you may be able to evaporate it off. So what we're trying to do is get this equilibrium set up. And so what we want to do in a recrystallization is that we want to create a so-called saturated solution of the compound at high temperatures. And if that solution is saturated, meaning that we have the maximum amount dissolved, then when we decrease the temperature, we'll shift it back to the not dissolved side. In order for this to work, not only do we need to play with the temperature, but we also need to select a solvent. And what you want in an ideal recrystallization solvent, first of all, it's going to make your life a lot easier if the boiling point of the solvent is less than the melting point of the compound, because that's going to make it very difficult to melt as opposed to dissolve the compound. If the solvent boiling point is higher than the melting point, then you have to pay a lot more attention so as not to melt the compound. And if you melt the compound, then it oils out and it can be kind of a nuisance to get. The other characteristic you want is that you want a certain solubility profile with temperature. What you want is this. You want something that's relatively insoluble at low temperatures and relatively soluble at high temperatures, because that's going to make it easier to shift that equilibrium back and forth. If it doesn't dissolve particularly well at any temperature, you're going to have to use a lot of solvent, and then you're not going to have a shiftable equilibrium. Same exact thing if it's too soluble, then again, you're not going to be able to get the equilibrium going. So you kind of want this Goldilocks effect of the solvent, which has just the right solubility profile for the compound that you're using. And in this particular experiment, they tell you what solvent to use. They tell you to use methanol. Eventually, you get to learn how to try to pick a recrystallization solvent. And when we do the aldol lab, you get to play with that a little bit. So again, the mission in a recrystallization is to create a saturated solution of a compound at high temperatures. And the way you can go about this is you're going to take, that's supposed to be an Erlenmeyer flask, and you need to heat it somehow. For a compound like methanol that is somewhat flammable and also has a somewhat low boiling point, I would use either a water bath or one of those impromptu steam baths. There's a link to what I refer to as the ghetto steam bath. If you go back and you look at my webpage for Chem 24, the main webpage, and lab cleanup, lab equipment, steam bath. And so there's a way that you can set up, as I said, a casual, impromptu, or if you prefer, ghetto steam bath. So should you ever actually get to do lab again, there you go. So I'm just going to put heat safely. And so you're going to have your solid in here. And you always want to use, I prefer a boiling stick over boiling stones, because when you're done, you can just take the boiling stick out and it's gone. You have to fish the boiling stones out, so the boiling stick is a little bit better. And then, this is the tricky part, you need to add just enough solvent so that it's dissolved at this higher temperature. And so one approach to doing this is that you can add a small amount of solvent to start, and then you're going to warm that up and then gradually add more of the solvent while you continue to heat. And so this is a little bit of a patience game. You have to add the solvent, let it warm up, add more solvent, let it warm up, because you don't want to add too much. You want to get kind of to that just right stage. Because even, going back here, even if you're at this perfect saturation point, the nature of an equilibrium is always going to be that you're always going to have some dissolve no matter what you do. No matter what you do, so you want to maximize your yield. So you gradually add more and more solvent while you heat it, and you want to do that until it just dissolves. So in other words, kind of like a titration, you add that last drop of solvent and it dissolves. So you're going to add just enough to get it to dissolve. And once you're done, once you've reached that point, you don't have to stare at it, you don't have to heat it. Just remove from the heat. And if you've done a good job, sometimes it'll actually start to crystallize out almost immediately because you're effectively lowering the temperature. So there are cases where students, want to show me their recrystallization, and they pull it off the heat to see, to say, oh, did I really get it dissolved? And by the time they walk over to me, it started to come out of solution, and that's actually a good thing. So you're going to remove it from the heat and let it go to about room temperature. You don't want to let it cool down too rapidly, because when it does that, what happens is the crystals form rapidly and they tend to trap impurities. And since the whole objective here is purification, that's a bad thing. So let it go to about room temperature. I'll sometimes tell students that they would willingly, with their ungloved hand, grab the bottom of that flask and hold on to it for a minute. Maybe it's cool enough. And then you want to cool it in either ice or an ice water bath, making sure that you have things set up so that it doesn't tip over. And students often ask, how long do I leave it in this ice water bath? And what I'll tell them is leave it in there, look at it, then come back, a couple minutes later and look at it again. And if it doesn't seem like you've made any more crystals in that time, you're probably good to go. So what you're going to have now, hopefully, is you've got your Erlenmeyer flask, you've got liquid in there, you've still probably got your boiling chip in there, and you've got your crystals floating around in solution. And they actually show that really nicely in the video of this particular experiment. And the deal here is that the impurities are in solution. And so you need to do something active to remove the solvent or the solution. And so if you just were to let this passively evaporate, you would have effectively done nothing, because you come back the next week and you haven't evaporated the impurities. So what you're going to do is a vacuum filtration. And the apparatus that you use for that depends on your scale. If you have a smaller scale, you might use the Hirsch funnel that's in your lockers. For a larger scale, you'll use a Buchner funnel. It's kind of a judgment call. You don't want to overwhelm the Hirsch funnel, and you don't want the Buchner funnel to overwhelm your product. As you're doing the vacuum filtration, it is okay to use a small amount of solvent to help transfer it. And you also want to rinse the product with that same solvent. And the solvent that you pick, you want is one in which the product doesn't dissolve. It's pretty disheartening when you've gone through your whole recrystallization and you wash your crystals and they all disappear. Generally, what will work quite well for a solvent is whatever solvent you use in the recrystallization, because you know that that solvent is going, is one in which the compound doesn't dissolve when it's cold. And so you can take that solvent, you can use it to help in the transfer, you can use it to rinse the product. I generally advise students when they do a vacuum filtration to moisten the filter paper. You can use it for that, all of those. And the colder the better. And so that's why in the procedure, I'm not sure, I don't remember about the video, but in the procedure, they use cold methanol for this because, again, it's less soluble in cold methanol. One more word to the wise. You've already used your vacuum filtration setup once for your crude product. You always want to start with a clean setup when you go to do your vacuum filtration for your purified product, again, in case something goes wrong. If your product ends up going into the filtrate at the bottom, and there's junk in there from before, that's a much bigger problem than if